The future of data systems is not one perfect database. It is many systems working together. Welcome to this explainer. Today, we're pulling back the curtain on why we are literally unbundling the database and how modern data pipelines actually work under the hood.
You know, that era of just throwing everything into a single, one-size-fits-all relational database? Yeah, that's officially over. But to really grasp where distributed systems architecture is heading, we've got to look at exactly why that old monolithic model just flat out broke under the weight of modern scale.
As our applications scale up, we have to stop trying to force every single piece of data through one magical system. Back in the day, you might have tried to use your primary database for high-speed transactions, full-text searching, and heavy analytics all at the exact same time. But reality just isn't that simple, right? Transactional workloads, your OLTP, they need row-level locking and super high concurrency. On the flip side, analytical workloads, or OLAP, demand column-oriented scans and massive aggregations. If you try to do all of that in one monolithic piece of software, you're practically begging for resource contention, locked tables, and huge bottlenecks. It's just the physics of database design. Optimizing for one access pattern inherently degrades performance for another.
So, let's dive into part 1, beyond one database, and into the unbundled reality.
Instead of having a single box trying to handle everything, modern architecture actually puts your application code right in the center as the orchestrator. It's routing read misses to a blazing fast in-memory cache like Redis, writing core state changes to a highly durable primary database, updating full-text indexes like Elasticsearch for those complex user queries, and pushing asynchronous tasks out to a message queue. At this point, you're not just an application developer anymore. You are a data system designer, stitching specialized, distributed tools together to handle massive throughput.
What we're effectively doing here is turning the database inside out. Instead of hiding all this functionality behind a massive, rigid SQL interface, we're treating distributed caches and search indexes as materialized views of one central organization-wide dataset. The internal subsystems of a traditional database, think secondary indexing, query planning, the write-ahead log, they are literally being split apart. We're replacing them with specialized, independent tools that continuously communicate across the network.
Now, to actually connect all these unbundled pieces, we need a seriously robust transport layer, and we integrate them by processing data in two very distinct ways: handling finite, historical files in massive chunks and managing the continuous real-time flow of event streams.
When we move data between systems to create our derived outputs, we really have to weigh some exact engineering trade-offs. On one hand, batch processors like Hadoop, MapReduce, or Spark absolutely excel at parsing massive, bounded historical datasets, and they output derived files on a scheduled basis. They maximize throughput, but at the cost of high latency. Conversely, stream processors like Kafka or Flink operate on unbounded, essentially infinite data, which gives you incredibly low latency, real-time derived streams. And while the lines between these two paradigms are constantly blurring in modern architectures, together they form the circulatory system of our whole unbundled ecosystem.
Moving on to part 2, the power of data flow. This is where we transition away from treating databases as passive variables and step into the highly reactive world of data flow. Think of modern reactive streaming systems kind of like a giant spreadsheet. When one single cell of data changes, every downstream cache or index updates automatically. In a traditional database, you actually have to actively pull the system to see if a state has changed. It's completely passive. But in a data flow architecture, we get this beautiful inversion of control. Pulling is dead. Instead, your application code responds to state changes in one place by instantly and automatically pushing those changes downstream to every specialized system that actually cares about that data.
Let's take a look at the write path. When a user updates a document, that event streams asynchronously behind the scenes. It flows continuously through some pretty heavy transformations, things like linguistic analysis, stemming, tokenization, vectorization, to proactively build a derived search index. And the best part? All of this computational heavy lifting happens entirely independently. It never blocks or slows down that initial user's HTTP request. Meanwhile, the read path is executing search queries against this newly derived state. This shows us exactly where the complex asynchronous write path meets the blazing fast user-facing read path. The derived dataset, in this case our highly optimized search index, is the meeting point. It represents a very calculated architectural trade-off. We are intentionally doing the heavy computational lifting proactively at write time, precisely so we can guarantee those lightning-fast microsecond lookups at read time. If we track the journey of a single data event, you can see this end-to-end flow in action. First, an event. Say, a user clicking a checkout button is captured immutably in an append-only log like Kafka. Second, a stream processor applies business logic and joins to that data while it's in transit. Third, the resulting state is used to instantly update a materialized view in a fast key-value store. And finally, a client observes that newly derived state updating live right on their screen. It is a continuous, fully reactive loop. All right, part 3, ensuring system correctness and handling faults. Because with data flowing asynchronously across dozens of specialized tools, we have to confront the harsh engineering reality of distributed systems, ensuring correctness when things inevitably fail. Keeping these distributed systems accurate requires some pretty strict design principles. We really have to rely on the end-to-end argument, which means passing unique request IDs all the way from the user's client device deep down into the storage layers. Why? Well, because networks stutter, garbage collection pauses happen, and systems are going to retry requests. By enforcing constraints and continuous verification at the edges, and by generating idempotency keys right at the client level, we can seamlessly suppress duplicate requests. That way, we maintain total integrity even during a partial network partition. Historically, engineers relied on painfully slow distributed transactions, like two-phase commits, to keep systems in sync. But let's be real, distributed locks absolutely destroy throughput. Today, modern architectures achieve correctness through asynchronous data flow paired with duplicate suppression and idempotence. If a stream processor crashes and restarts, yeah, it might process the exact same message twice, resulting in at least once delivery. But if your database operations are designed to be idempotent, that duplicate processing has zero impact. The resulting state remains perfectly correct, and your system stays infinitely more scalable than if you were relying on global locks. And to ensure this integrity at scale, the future is pointing straight toward continuous automated verification. As our systems fragment into these highly specialized pipelines, we can leverage cryptographic auditing, using techniques like Merkle trees and distributed ledgers to mathematically prove that a downstream derived dataset accurately reflects the original immutable event log. It's a way to inherently build observability and absolute truth right into a highly decentralized architecture. Now, as we master this sea of derived data, and really perfect our reactive programming models, we inevitably leave the safety of pure engineering behind. We're sailing into the uncharted territory of real-world human impact. We've figured out the architecture, the scalability, the fault tolerance, but now we have to figure out the consequences of what we've built and how these massive systems actually intersect with society. Which brings us to our final section, privacy and real-world trade-offs, or simply doing the right thing with data. As system designers, it is so important that we talk about the broader impact of our work. Data systems aren't just abstract math. They are engines that actively shape human experiences. For example, if a predictive algorithm is trained on biased historical data, it won't just reflect that bias, it can create a feedback loop that mathematically enforces it. Furthermore, that incredibly granular event tracking we rely on to optimize our caches and debug our pipelines, it can easily become a tool for highly invasive surveillance. It really forces us to consider the fine line between system observability and the total erosion of user consent. So I'm going to leave you with this final critical question. Our systems may be perfectly integrated and highly scalable, but as engineers, are we building a world we actually want to live in? We possess the tools to unbundle databases and process massive event streams in real time, but we must consciously choose to build architectures that balance raw technical performance with privacy, ethics, and a deep respect for the end user. Thank you so much for exploring the future of data systems with us in this explainer. Keep learning, design responsibly,